So today in external flow, we're just going to look at flow over a flat plate. Next time we'll look at flow over other objects. But it turns out the solution process is similar. You just use different experimental results usually. Flow over a flat plate is a little different because the Reynolds number is a local Reynolds number. It's changing as you go along. And also for the laminar case, there is actually a solution, an Navier-Stokes solution for it. So flow over a flat plate again will look something like this as far as this is your boundary layer. So this is where your velocity is changing, right? And we're going to call that boundary layer thickness delta. Okay, and eventually, so this is what it looks like laminar. Eventually you'll start to get some transition little unstable regions, and then it's going to go turbulent. Okay, so turbulent out here. Okay, so here where it's laminar, nice smooth velocity profile. Things aren't so crazy. This is more difficult to solve than your pipe flow solution because u is a function of x as well as y, and also v is not equal to 0. Okay, so it makes it a little bit more difficult. But someone has come up with a solution, at least for u. Boundary layer thickness, then, we have to define it. Theoretically, you could go as far away as you want from this plate, and the plate would still be affecting the flow. But you got to stop somewhere. So what we do is define the boundary layer thickness as the region up to 99% of the outer flow. Okay, so that's where you come up with that delta. Okay, and delta equals the boundary layer thickness. Okay, drag on these flat plates mainly due only to pressure, not shear. Okay, so for laminar flow, we're going to look at laminar and turbulent, but for laminar flow, some guy named Blasius, who was a PhD student of Prandtl, actually first used some tricky math and was able to solve the Navier-Stokes equations for this. He used some non-dimensional parameters and was able to figure it out. So that's good. We don't have to try to figure it out ourselves. It is pretty tricky. But this laminar flow solution is valid up to our critical Reynolds number of 5 times 10 to the 5th. Okay. So whenever we calculate a Reynolds number and it comes out that over that whole plate we have a lower Reynolds number than 5 times 10 to the 5th, we can use these laminar solutions that Blasius came up with for us. Okay, so we're still going to use some non-dimensional parameters, even though we're talking about a laminar flow solution. And if you do the dimensional analysis and you're talking about boundary layer thickness, which is sometimes what we're trying to find, you're going to come out with delta, boundary layer thickness, is a function of all these other things, and if you look at that, guess what? You get Reynolds number in there. So it comes out to be a function of Reynolds number. And it turns out then if you plugged in the equation for Reynolds number here with an x in it into the 1/2 power, multiply through by x, you're going to get that delta is proportional to the square root of x for laminar flow. Okay. Another thing, once we have Blasius' solution for u, we can figure out what the shear stress is. And the shear stress, remember, is mu du dy approximately. So at the wall, it's going to be mu du dy at y equals 0. Okay, again though, this is going to change with x. So u is not, it's not fully developed here like we had in a pipe flow. So it's going to change with x. So, but we can use this and Blasius' solution to come up with an exact equation for shear stress. Okay, so let's look at x. X is in the denominator here. So as we go along the plate, x gets bigger, which means shear stress gets smaller. Tau at the wall actually decreases. And that's because du dy gets smaller. Okay, and if you look back at the picture, yeah, in here the velocity is going to be changing with respect to y a lot faster to get back up to this outer flow. So if you look at the wall, it's going to be a bigger slope. You got to remember slopes are backwards in these. All right, so that's shear stress, but most of the time, again, we are going to use non-dimensional parameters. We're not going to normally just straight solve for shear stress. So what we do is use skin friction coefficient, and the skin friction coefficient, it's a lot like what we had for a friction coefficient for pipes. It's just our non-dimensional form of shear stress at the wall. So CF is tau wall over 1/2 rho u squared. Okay, and you can just take our equation for tau and plug that in, and what you get is this skin friction equation, and you got to just remember that this is for laminar only. And all these things, the tau w and the CF, those are both functions of x. So that's changing along the length of your pipe. Okay, usually you're not looking for, at any particular x value, what is the shear stress, what is the skin friction? Maybe, but usually you want the whole drag for the whole side of the plate. Okay, what is the total drag on this side of this plate? And whew, word messed this one up, didn't it? But at any rate, you can still see this is supposed to be a dx. This is an L. Okay, and we are going to try to find the total drag on this plate if the flow is going this way over this plate. So if the width of this plate equals b, what we want to do here in order to get this total drag, knowing that the shear stress is changing over the whole length of this, what we need to do is find the shear stress at any point and then integrate over that whole length. So if you remember, a shear stress is a force per unit area, so the shear stress times the area gives you that force, and that's what we're looking for, this drag. So d, the drag, for that little section there, is going to be tau at the wall for that little section, times the width times your dx, because your dA is now going to be dA equals b dx, right? So the total drag on the side, then you got to just integrate from 0 to L, tau wall, b dx. Well, we had an equation for tau at the wall for laminar flow. 0 to L, 0.332, rho to the 1/2, mu to the 1/2, and those are just constants. U to the 1.5, also a constant, over x to the 1/2. Okay, b dx. That's something we can integrate. And if we do integrate it, what we get is drag 0.664, rho to the 1/2, mu to the 1/2, square roots in other words, u to the 1.5, b, l to the 1/2. Remember, that's laminar only. Okay, so there's an equation we can use for drag if we have laminar over our whole plate. Usually we don't use that though. Usually what we do is use the drag coefficient, because the drag coefficient is what we end up using for turbulent flow as well, so it's just makes it a little easier to stay consistent with your solution method. So the drag coefficient, again, it's your non-dimensional way to express the drag force, kind of like the skin friction was a non-dimensional way to express the shear stress at the wall. So our drag coefficient is just drag over 1/2 rho u squared a. Okay, and the area that we're going to use for a flat plate is what's called the planform area, or the top, because shear stress or skin friction is really what's causing the majority of the drag here. Okay, so we will do the whole surface area there when that's the case. So plugging in for the area and for the drag that we just found here, we're going to get then a CD for laminar flow is 1.328 over Reynolds number to the 1/2, or the Reynolds number is at the length of the whole plate. Okay, so Reynolds number, the length of the whole plate, that means rho u L over mu, or just UL over nu. Okay, so that means at the end of the plate. This only works if it's laminar over the whole plate, all the way to L. So F over an entire flat plate. Okay, if it switches to turbulence, then it's no good. We got to do something else. Okay. Example here. Glycerin. So glycerin's like your corn syrup. It's very thick. It's going to have a high viscosity, so it's more likely to be laminar. Flows at 25 meters per second over a flat plate, 2.5 meters long, 1.25 meters wide. Sorry about these. Wow, it looks like I'm cussing all over this picture, but we have all the numbers we need. Mu here equals 1.5 kilograms per meter second, and rho 1264 kilograms per meter cubed. Okay, so first we got to find delta at the end of the plate. So at x equals L, or 2.5 meters. In order to do any of these problems, the first thing you want to do, if you can, is find Reynolds number. Okay, so because you got to decide if it's laminar or turbulent to decide which ones to use. Glycerin is probably going to be laminar, although that's really, really fast. So this is going to be a high force. So if laminar at x equal L, then it must be laminar over the entire plate, because the Reynolds number is just going to be smaller at smaller x values. So if it's laminar at x equals L, laminar over entire plate. So you want to find the Reynolds number at L. So the Reynolds number at L, rho UL over mu, comes out to be 5.27 times 10 to the 4th. Okay, well, is that laminar? Don't think 2300, because that's not your critical Reynolds number. Critical Reynolds number is 5 times 10 to the 5th. So this is less than 5 times 10 to the 5th. So this is laminar. Luckily, because that's all we've done so far is laminar. So part A says delta at the end of the plate. We can use our delta equation that we found for laminar flow. Came from Blasius's solution, and that was 5 over Reynolds number to the 1/2 was equal to delta over x. So for L, delta over L equals 5 over Reynolds number L, which we already calculated, to the 1/2. And if we go ahead and just plug in, we're going to get delta equals 54.5 millimeters at x equal L. Okay, that's just solving this equation. All right, so there's part A. Part B is drag force on the one side. Okay, so two ways to do this. We had an equation for drag, so I could just go back up and plug into this equation for drag. But that's not the way we do it for turbulent flow. So what I'm going to do instead is calculate a coefficient of drag, which is actually pretty easy because I already have Reynolds number at L. And once I have that, then I'm going to use that to calculate drag, because I also know that coefficient of drag equals drag over 1/2 rho u squared A. Okay. So for laminar over the entire plate, I can say CD is about equal to 1.328, not about equal to, it is equal to, over Reynolds number at L to the 1/2. Okay, so if I just plug in Reynolds number of this into that Reynolds number, I'm going to get 5.787 times 10 to the minus 3. And that is going to be drag over 1/2 rho u squared A. Okay, again, A for this, A is going to be your width times your length, which in this case is 1.25 meters times 2.5 meters. Okay, so plugging all that in, I'm going to get drag equals CD times 1/2 rho u squared A, comes out to be 7,143 newtons. Really big. Okay. And again, the alternate method would be just to plug into that drag equation that you had for laminar flow. So stop here and do quiz questions 3 through 5.